video is going to discuss molarity, which is a way of describing how concentrated a solution is. There are many ways of describing the concentration of a solution, and different ones are better for different purposes. But for chemistry, molarity is often the most useful one. Here's why. It's the concentration described in moles of solute per liter of solution. That's what molarity is. And liters of solution is pretty easy to measure. It's easy to measure volume for a liquid. And moles is what we often use in chemical calculations, like stoichiometric calculations. So this is actually a pretty natural unit to use. It's abbreviated capital M, and when you see something like, let's say, 12 moles per liter, it would be abbreviated 12M, and you'd say that 12 molar. That's how you pronounce that. And definition, just moles per liter. And this is moles of solute per liter of solution, not per liter of solvent, but for total liter of solution. One of the reasons that's very handy is because you can use it in dimensional analysis to solve all kinds of problems. Like, for example, let's say you wanted to know how much of a 0.250 molar KCl solution would provide 0.0250 moles of KCl. Here's how you could do this. Make your starting point 0.0250 moles of KCl. The ending point, we want that to be liters, or volume. And here's the factor that we can use, molarity. 0.250 moles of KCl are in every 1 liter of this solution, by definition. With moles of KCl canceled, you can now find that it's going to be 0.100 liters, or 100 milliliters, that will provide us with this many moles. Well, how do you make these solutions? Two ways you can do this. You can prepare a solution of known molarity by dissolving a solid solute. This is one way to do it. Here are the steps. The first thing you want to do is determine the mass of solute that would be needed to make a liter of solution. Well, if you know how many moles are going to go in a liter, and you know how to convert moles to mass, that's not too hard to do. You just need to know the molar mass. Like, let's say, for example, you wanted to make this 500 milliliters of a 0.10 molar NaCl solution. To find out the mass that would be in 1 liter, I would just take my molarity, 0.10, and I know that 1.10 moles, that means, of NaCl would be in a liter. But I want to know mass, so I'll multiply by the molar mass of sodium chloride, which is 58.443 grams per mole. And this tells me that I'm going to need 5.8 grams of sodium chloride in an entire liter. I don't want to make an entire liter, so the next step is I have to take that quantity and multiply it by the number of liters I'm trying to make, the number of liters in my volumetric flask. So in the example that I'm working on here, I want to make 500 milliliters, which is a half a liter. And I want to multiply that by the 5.8 grams of sodium chloride I need per 1 liter. By doing this, I can determine the amount of NaCl I'm going to have to actually put in my flask, which comes out to 2.9 grams of sodium chloride. Next, I'd weigh out the mass of that solute and put it in the flask. So I'd weigh out 2.9 grams to make my 500 milliliters of 0.10 molar NaCl. And then the last step is I'd fill the flask right up to the mark that tells me when I have exactly 500 milliliters. Halfway through, when I still have room to slosh it around, I'll swirl it a bit to make sure that the salt dissolves, and then I'll fill it up to the top. So let's watch a little video of that process in real life, and then we'll talk about another way of creating a solution of known molarity. Well, in this example, I want to make 500 milliliters of a solution that is 0.10 molar in sodium chloride. The first thing I have to do is figure out how much of this am I going to have to weigh out if I wanted to make an entire liter. Well, I know that I want 0.10 moles of NaCl for every liter. That's going to be a starting point. What's the molar mass of sodium chloride? That's the next thing I need to know. Well, I can calculate it, or I can look it up. Here's my bottle of sodium chloride, and it lists the formula weight, which is 58.45 grams per mole. That's the molar mass. So I'll put that in here next, 58.45 grams per mole. Moles would drop out of this, And when I multiply 0.1 by 58.45, I get 5.845 grams. So that's how much sodium chloride I would put in a liter of this solution. Now, I'm not going to make a liter of this solution. I'm only going to make 500 milliliters. So my next step is I figure out how much I really need in my solution by taking the mass for a liter, 5.845 grams, and multiplying that by the number of liters, because this is grams per liter. 500 milliliters is 0.5 liters. And I need two significant figures there because the volumetric flask I'm using is that accurate, and also that's the precision that I need to get three significant figures on my volume. Liters now cancel, and this tells me how many grams will I actually need in my solution. So now I calculate 5.845 times 0.5, and I get 2.923 grams. Now I'm going to weigh this out on a balance that only weighs to the nearest hundredth, so 2.92 grams is what I'll weigh out. I'll start out by zeroing my balance, make sure that it's reading 0, and then I'll place a weighing boat on the pan and zero it out again. Next, I'll take a spoon and I'll add a little sodium chloride to the weighing boat. And I'm getting close. I need 2.92. Put a little bit in at a time. And I've overshot. So I'm going to scoop a little bit out. Still too much. Take a tiny bit more out. Now I'm under again, and I want to add just a few granules at a time till I've got it right. Okay, I've got 2.92, 2.91. You can see there's a little bit of float there. That's to be expected. And if I try to mess with it and get it any closer than that in the hundredths place, it's probably not going to work out right. So there's my reading, 2.91 grams. Okay, that's how much goes into my flask. The flask I'm using is a 500 milliliter flask. The flask I'm using here is a 500 milliliter flask, and you can see that it's calibrated to contain plus or minus 0.20 milliliters. So this is a very precise vessel. This is the kind of thing that you use for creating solutions of known molarity. Now I'm going to make sure that all of my sodium chloride makes it into the top of the opening of my flask. Now you can see in the bottom I've got my sodium chloride. The next thing I have to do is add water to it. I'm pouring water in here, and you want to use distilled water because you're trying to make a solution just of sodium chloride, not a solution that contains the other things that are in tap water. I'm going to swirl my solution around to get the sodium chloride to dissolve while I still have room in the flask for it to swirl. So you can see that I'm swirling here. And at this point, the salt is all dissolved. And now I begin filling up the rest of the flask to the mark in the neck of the flask that indicates that I've reached my full 500 milliliters. When I get near the mark on the neck of the flask that indicates full volume, I'm going to slow the rate down a lot at which I'm adding the water. And in fact, as I get very close, I'll switch over and begin to just add drops at a time. If you look very close, you'll notice that the surface of the water isn't flat. This is always the case in glass containers like this one. It forms what's called a meniscus, and that's this curved, kind of sunken in the middle shape. I want the bottom of that meniscus to be right on the line. So with an eyedropper, I'm now adding small volumes at a time until I reach the spot where the meniscus is right on the line. Now, my volume is 500 milliliters, as near as I can possibly measure it, and I've got my solution created. Another way I can prepare a solution commonly is by diluting a solution that's more concentrated. To do this, the first thing you want to do is find the volume of the concentrated solution that you'd need. Like, for example, if I was going to make 250 milliliters of a 3 molar HCl solution by diluting a 12 molar H solution, I'm just going to have to add water to the HCl. The trick that we use is something called the dilution solution. I know that the molarity of a solution times its volume is the number of moles of solute that are in that solution, just sort of by the definition of what molarity is. So in the concentrated solution I have a certain number of moles, but in the dilute solution I have the same exact number of moles, because no moles of solute comes from the water that I've added. So that means the molarity of the dilute solution times the volume of the dilute solution is equal to the molarity of the concentrated times the volume of the concentrated. So if I take this little equation here and solve it for volume of concentrated, I find that I have the molarity of the dilute times the volume of the dilute divided by the molarity of the concentrated solution. Well, let's apply that here. I've got a volume of concentrated solution that would be equal to 3.0 molar times the volume I want, 250 milliliters, divided by the molarity of my concentrated solution, which is 12 molar. Do a little canceling here. This is going to be 250 milliliters divided by 4, which will come out to 62.5 milliliters. So the next thing I do is I pick up my flask and I put the concentrated solution in the flask. Now, if I'm creating an acid dilution, like I would be in this case with a strong acid, I don't want to put that straight in the flask and then add water to it. And there's a reason for that. There's going to be a violent reaction that happens between the acid and the water as the water begins to pull the acid molecules apart and spread them further in the water. I want that violent reaction to happen in the bottom of the flask, not at the top where it can splash out and burn me or just change the concentration of my solution. So I'm going to put a little bit of water in there first. So if it's an acid, put some water in the flask first to avoid this. Always add acid to water, never add water to a concentrated acid. Then I'm going to dilute with water until I'm pretty close to the mark on the flask, but not quite there. After that, I'm going to cover the top, and then I'm going to just flip it upside down several times, carefully holding the stopper in so that it doesn't leak, until I can't really observe any mixing taking place. And you'll be able to see this kind of a swirling pattern of two different density solutions, even if they're both colorless. When it doesn't look like mixing is happening anymore, then I'm going to pull my stopper off and then dilute the rest of the way to the mark on the flask, being very careful to stop right at the mark. Once I've got that, I'll invert it a couple of times and mix again, and then I'll be done. So let's take a look at a little movie of how you would do this in real life. My objective here is to make 250 milliliters of an acid solution that's 3 molar in concentration hydrochloric acid. Now I'm going to make this from a hydrochloric acid solution that's 12 moles per liter, or 12 molar, and I'm going to do it by diluting it with water. So I'll make note of that here. Now I'm going to find the volume of concentrated solution that I need by using a technique that's sometimes called the dilution solution, or sometimes it's called the solution-dilution solution. What it is a very simple formula that just says that molarity times volume is equal to number of moles. And since the number of moles in the concentrated solution is the same as the number of moles in the dilute solution, because all I've done is add water, which contains no moles of solute, I can set them equal to each other, and that's the dilution solution. The molarity of the concentrated times the volume of the concentrated is the molarity of the dilute times the volume of the dilute. So I'll solve this equation for the volume of concentrated that I need. It's molarity of dilute times the volume of the dilute divided by the molarity of the concentrated. So in my situation, I can put numbers to this. 3 molar is the molarity of my dilute solution I'm going to make. I want to make 250 milliliters of it. And the concentrated solution had a molarity of 12 molar. Well, 12 divided by 3 is 4, so I really have 250 divided by 4, and that comes out to 62.5 milliliters. That's how much concentrated hydrochloric acid I'm going to need to create my 250 milliliters of dilute hydrochloric acid. One of the tools I'm going to need is a volumetric flask, so I've selected a 250 milliliter volumetric flask, and this is calibrated plus or minus 0.12 milliliters. So that's about as precisely as I can measure 250 milliliters. And for the acid, there are a number of tools that I could use to measure it out. Because not a lot of precision is demanded, I'm just going to use a simple graduated cylinder. So I've taken some 12 molar hydrochloric acid and I've filled it up so that the volume is 62.5 milliliters. You probably can't see the marks on this plastic flask in this video, but I've filled it up to 62.5 milliliters. In this case, what I'm diluting is a strong acid. And when that's the case, you always want to put a little water in the bottom before you add the acid. This is because there's going to be a fairly violent reaction that occurs between the two, and I want that to happen at the bottom of the flask, not at the surface of the water. So after adding a little bit of water, just to give it some volume, I now pour in my 62.5 milliliters of hydrochloric acid. I'm going to swirl it around to just give a little preliminary mixing. And at this point, with a concentrated solution, you're going to start to feel a little bit of heat probably, or in some cases it'll start to get cold depending on what you're dissolving. Right now this flask feels a little warm. Now I can continue to add more distilled water to my flask, and I'll keep doing that until I get close to the mark in the neck of the bottle that indicates full volume. Once I've filled it up so that I'm fairly close to the mark but not quite exactly there, I'm going to take a stopper and put it in the mouth of the flask. I'll put my finger over it for safety, and then I'm just going to invert this flask and give the solutions a chance to mix. I'll do this several times. You probably can't see this in the video, but most of the time when you mix two colorless solutions that have different densities, you'll see this swirly pattern inside the flask that indicates that they're mixing. After inverting a couple of times, I'm now confident that it's pretty well mixed, and if any shrinkage or expansion took place, it's done happening, and now I can just fill it up to the top and not worry about going too far. Now I'm going to finish this off by very carefully adding with a pipette a few drops of distilled water until the meniscus of my solution is right on the line that indicates 250 milliliters of volume. Next, I'm going to stopper it and I'll invert a couple more times just to make sure that last little bit of mixing is done. And now I've got my solution complete.